Hello everyone, today Moritz Wegener will be presenting this session. Moritz, over to you.
Hey, thanks to all of you. Actually I will start sharing my screen. And now you should all see the slides of my presentation. So if we don't have anything to do anymore, I will just start with my presentation today. So yeah, first of all, thank you very much for joining my presentation today. And today I will talk about two things I really like to talk about and I really enjoy. And on one hand is about graph databases and how we could build recommendation systems. And we are doing this today in the example of some kind of wine data set. This is why we choose this title. That's from my side. My name is Moritz. I work for the Advantage. We are a software and consultancy company based in Cologne in Germany, and we are an official Neo4j partner. So we are cooperating with Neo4j. I work there as a data scientist, and I'm currently handling topics about machine learning and about graphs. So what do we want to talk about today? I would just want to give you a short introduction into how we could build recommendation systems on the example of wine data. So we will first make a small definition of what is a recommendation systems and what problems you want to tackle. And I will give you a short introduction to the data set we used. Then we will talk about the funny stuff, so how we actually modeled the recommendation system. And I'll show you some matrices how we could evaluate recommendation systems. So let's start with the problem. Actually, most of you are using recommendation systems in the everyday life, even if you don't recognize it. For example, we have Netflix. And if you take a look at Netflix and how you normally use it, you are not searching for movies or series anymore. Netflix is just giving you the stuff that they think is interesting for you directly to you. And this is very comfortable for the user because you don't have to think about what you need to watch. You just have to think about, okay, what is Netflix recommending me and if you like it or not. Of course, this is not limited to Netflix. You can also take a look at Spotify. They are also recommending playlists to you. This is an example as playlist I got recommended. I'm quite very like hip hop music, so I get recommended a playlist with some cool new songs. And this stuff is not only limited to digital goods. You can also use it for physical goods. So if you take a look at an example of wine, we can have a wine retailer, and you just drink wine there, and you will get recommended wine that you like. And this is, as I said, quite comfortable and very good for the users. So what is the benefit of a good recommendation system? On one hand, we talked about this before, it's an improvement of user experience. So when we take a look at the example of Netflix, we see that there's almost about 80% of all series that users watch on Netflix come from recommendations. And this is quite heavy. Also, this gives you a strong customer loyalty. So good recommendations, of course, lead to high satisfaction, and your customers are quite happy. So they are ultimately less to churn. So they are not using any other services. On the other hand, if you don't have that many customers or customers joining your platform which are not paying for your service at the moment, it increases your conversion rate. So if they like your recommendations, it's more likely that they are buying your product, which leads to higher conversations. And in the end, all of this leads to increased sales. And since most of us are working for business companies, of course, this is at the end the aim we want to do. But what are challenges when we are talking about recommendation systems? And we talked about we are doing it on data. So when you talk about recommendation systems, you often analyze and filter a huge amount of data. And these filtering and analyses have to be defined by some people and have to be developed. So therefore, of course, a recommendation system is investment which you have to pay. When we talk about huge amounts of data, we often also talk about scalability and speed. So recommendations based on large data often require long computation times. It can be quite costly also to compute stuff like this. So you need to be aware of this. And also we can have the opposite of what we have done before. So if we are not taking good recommendations and giving the users a lot of irrelevant recommendations, we get the opposite of it. So it leads to lower customer satisfaction and at the end to more churns and to less conversation rights. And also recommendation systems can be quite biased. So you have to be aware of this, because if you're always recommending the same stuff to all the users or giving it too high, it's also not good for your recommendations. So let's talk about the data set we use for our recommendation engine. We actually built that on a real world data set. So we got like this X wine data set, which is publicly available on GitHub. And what's inside of this data set? So we have 3 different versions, and we used like the lower version, so the full version, where you have about 100,000 wines. Each of them has 17 selected attributes. You have 21 million ratings in a scale from 1 to 5 star. So you can think about the rating system similar to Amazon. 5 is the best one, 1 is the lowest one. And we have around 1 million anonymized users, so we don't have metadata for that. The cool thing about this is just that it's actually like a real world data set, so it's not some kind of AI generated stuff. So you can really see like real human behavior inside of it. So what information do we have for the wine? Of course, we have like a unique identifier for every wine and a name for the wine. And then we see like the attributes we have for the wine. We have, for example, different types of wines. So if it's a red wine or white wine, we have some kind of other attributes like what grapes are used in the wine, what meals are actually harmonizing with the wine, and for example, the ABV, which is how much alcohol is inside of the wine. And we see here that we have the majority of all of our variables are category variables or numerical variables. We can also take a look at the user reviews. So we see for each user, or each user has like a unique identifier as well. And we can see how each user ranked each wine on which date. So how could we now build out of this like a recommender system? And the idea of recommender system, we can divide that into 2 parts. So when we talk about recommender systems, we majorly have like 2 different approaches. On one hand, we have like content-based filtering, which we see on our left-hand side now. And on the other hand, we have like collaborative filtering, which we see on our right-hand side now. And maybe let's start with like the content-based filtering, which is the idea, or what is the idea behind it. So we assume we have like a user, maybe we call him Bob, and Bob likes a certain kind of wine. And what we now want to recommend to Bob is similar wines to the wine Bob has already drunk and hasn't drunk before. So we are first like trying to find out what kind of wine Bob likes. We are trying to find similar wines and we recommend it to Bob. That's the idea behind it. Now, if you think about how could we calculate like similar wines to the one Bob has already drunk before. And when we talk about similarities, we often talk about statistics, about math, and we need numbers for this. And actually, it's quite hard, of course, to calculate something like this just with textual data. So we have to find some kind of numerical representation for our wines now. And what we try to build up out of this is an embedding. And an embedding is like a numerical representation of all the features a wine has. So we want to build for each of the wines like a good numerical representation to compare them. An embedding is nearly a vector, so like a number of lists, and each number inside of the vector represents some kind of feature of the vector. But why do we want to use actually these vectors and build them for every wine? Because the cool thing about vectors is we can actually calculate similarities between vectors. So we have here like a very easy example. So we can calculate the cosine of the angle between 2 vectors. We see here like a 2-dimensional or 2 two-dimensional vectors. And we can see that the angle between them is like 60 degrees. So we can use the cosine value here, and we got like a similarity of 0.5. So actually, we are measuring how strong 2 vectors point in the same direction. And we can assume here that if 2 vectors are pointing into the same direction, they are like pretty similar. So if we are finding a good representation for the wines, we can like calculate similarities in a good way. But the question now is, how could we like build these embedding vectors? And we have different approaches for it, which I want to present to you now. So we have more classical approaches. For example, we can calculate the embeddings directly from the features. So for example, we have here different kind of encodings. We can first maybe start with the numerical values. So you see like that we have like the ABV value for every wine, and we can do some kind of feature scaling. So we try to bring the features of the numerical values between a value of 0 and 1. How do we do that? You can actually see here the formula. So we are calculating, taking the value of the first wine, like 7.5%, subtract the minimum of all wines, since we assume we also have alcohol-free wines in our data set, this is 0, and divided by the maximum of all wines minus the minimum of all wines. We can also make here the assumption that the second wine, so the 12% is the highest value here to keep it easy. And we can see that we are actually getting our first feature inside of the vector, which you can see on the right-hand side, which represents then the ABV value. For categorical values, we can use different approaches. On one hand, we can use one-hot encoding. So each of the actual characteristic inside of the feature, so we can, for example, take here the type, is represented as one value in the vector. And every time we have a value of 1, we are saying, okay, this characteristic is activated for the wine. And if we are saying, okay, we have a value of 0, we don't have activated for it. So for example, if we are taking the type, we can actually make one entrance in the vector for the sparkling wine and one for the red wine. So we are taking the second value here as the sparkling wine and the third as the red wine. And for the first wine, then we get a representation of 1 and 0 and get the second and third entrance in our vector. The last thing we can do for like categorical variables is like target encoding. So when we're taking all the vintages, we can, for example, calculate the average out of it and make some kind of target encoding for it. You see that we are calculated for the 2 wines. And again, we have to do min-max scaling because we want to bring the value on a scale from 0 to 1. And we got our last entrance for our feature vector there. Pretty easy and straightforward. We can also use some kind of text embeddings. So text embedding is another classical approach which we can use. And we can here represent each feature as a text. So we are taking like all the features from our first wine and just concatenating them and building like a string or a text. So we can see here in the example that we got for our first wine, we have like type equals to sparkling, elaborates equals to variety 100%, ABV equals to 7.5, and so on. So now we have like a representation of our wines as texts, and we are trying to use like a concept which is called sentence transformers. And sentence transformers are actually pre-trained neural networks to form semantically meaningful embeddings. So what does that mean? We are trying to build embeddings, and we are assuming here that the embedding we build are similar if the text that we put inside of the sentence transformer is quite similar. So if your text is similar, you are getting similar vectors. How does this actually work? So we are taking our text value. We are loading some kind of sentence transformer. We can use here the SBIRD library, which is quite famous, and choose the model. And we get like a representation as a vector. The dimension here, so how many entrances you have in the vector, actually depends on what model from SBIRD you are choosing. And here you can see that we have values inside of the vector, and these values are pretty hard to interpret by a human being. So we call these features latent features because humans can't really interpret it. The model can interpret it and has some kind of meaning behind it, but for human, it's very hard. So we are finished like with our classical approaches, and we can go on like to the graph approaches. But how do we do it? First, we have to think about now we don't want to store our data into tables like we have done it before. So we are going from the table representation to a graph representation. And how do we do that? Actually, we are modeling all of our wines here as nodes. So each of the wine is created as a node, and we are giving every of these wines a label. So the wine label in this case. And we can directly put properties on our wine. So for example, we will put the numerical properties of ABV directly into all of our wines. We can also model the rest of the features also as nodes. So we can give them labels and directly link them to our wine. This is what we call relationships, and the relationships also have some kind of labels. Since we can then like create for every grape that we have in our data set a node and can link all the wines which has this grape or where it's included to our wine. So then we are finished with the wines. Last but not least, we also have to include like the rating. So we are modeling each user as a node and giving them the user label. And we can add like a relationship between the user and all the wines. So every user node or every user which has rated some kind of wine, we can create like a connection between it. And we can also store properties, so the rating directly on the edge. So what can we do now like with this kind of network? And actually we are building this network to run some kind of algorithm on it. And this algorithm is a fast RP, so the fast random projection embedding. This is a graph algorithm to calculate embeddings for a given node. And how do we do that actually? We try to do it based on the graph structure. So we are using like the structure of the graph to build like good embeddings for the nodes. And since we can't use like everything which is inside of the graph, so we can't use all of the relationships and all of the properties and stuff like this because this vector will be too big, we try to achieve a massive dimension reduction. But what do we actually mean with graph structure? So what could we include? And for this, I give you like a short introduction into the library we use here. So this is from the graph data science library from Neo4j, and you have different kind of properties which you can use to actually configure how your algorithms work. So on one hand, you can choose what kind of labels should be inside of your graph structure. You can decide what kind of relationship types, so what kind of relationships label you want to have in your graph structure. You can, for example, also add a list of feature properties, so the features which are on the nodes, and give a list of it, which should influence like how you build your embeddings. And you can, for example, if you take a look at the bottom, you can also include some kind of properties which are on your relationships that should like influence your embeddings. Of course, you have way more configuration options, but we don't want to get through all of them. If you want to take a look at it, try to maybe take a look at the documentation. And yeah, all this algorithm is like based on a paper from 2019, which is linked like below. But now we know we have some kind of graph structure and how we could influence like the graph structure. And now it's quite interesting. How does this algorithm work like on a higher level? And for this, we can take a look at an example, maybe here from two wines. So here we have two quite similar wines. And why are these wines similar? Because they have like a lot of common nodes. So they share a lot of nodes, and they also share for this like a lot of characteristics, you can say. So these two nodes should be like similar. We can see that here we can add like a edge, which is called similar to model some kind of similarity between them. But how do we actually achieve that these two nodes are quite similar? And the idea behind this is that we are generating like random embeddings, so random vectors for all the nodes around them. And now we try to calculate like the embeddings for the Y nodes. And for this, we are taking a linear projection of all of the nodes, so of all of the embeddings on the nodes, which are linked to them. It's like averaging like all of these embeddings. And if you're averaging like all these embeddings and you share like a lot of embeddings, you have like also pretty similar embeddings directly on your node. And that is the idea behind it. We can maybe take a look at another example, which makes this maybe a tad bit clearer, because here we can see like a pretty unsimilar ones. So we can see also that they have like a lot of nodes, so all the characteristics are linked, and you only have like two common nodes. So your wines are not very similar, they are very different. And if you now think again like this, and you think like, okay, I take with now random embeddings for all of these nodes and averaging them, your two embeddings, which are on like your wines, are not very similar because they didn't share like a lot of nodes. So this is the way how you could like generate embeddings based on a graph. So now, how do we actually build now the content-based filtering? And the idea behind content-based filtering, if we take that back, is find wines that are similar to those we have already rated. And your similarity is based like on your attributes. But you do not only want to keep in mind how similar your wines are, you also want to include the rating you gave to the wine. And we made here an example. So when you take a look at the red relationships are the rating. And if they are like bolder, which means that their right rating is higher. So if we take, for example, a look at the right-hand side where we see the rating between the user and the wine, here we have a quite high rating. When we take a look at the left-hand side, we have like a medium rating for the wine. And we can do the same for the similarity. So we are modeling the similarity again as relationships, this time as the green ones. And we are again assuming if they are like more bolded, we have a higher similarity. So we want to keep both of this actually for the recommendation, and we have to calculate in this way for some kind of recommendation score. And the idea, for instance, that's an example, of course, if you want to do that in the real world, you have to talk to business people, how this should influence the stuff. But we, for example, calculated a recommendation score for each of the wines, which is linked as similar to, by calculating or multiplying 0.5 times the wine similarity score plus 0.5 times the assigned rating for the wine. So we are finished like with content-based filtering, and we can directly go into collaborative filtering. First, let me take a sip of water. So when we talk about collaborative filtering, we not anymore want to just like take one user. We also want to take like the opinion of all the users. And what is the idea behind it? We can again make it maybe by an example. So we have a user, maybe we call him Bob. And we have like a user, maybe call her Alice. And we now want to calculate or want to give recommendations to Bob. And the idea behind this that we want to know if Bob and Alice share like or have like a similar taste. So if Bob and Alice like the same wines, we can assume that they are like similar users. And now we want to recommend wines to Bob. And the idea behind that is that if we have like already wines which Alice likes, shows she has a similar type as Bob, we have a high chance that Bob also likes these wines because they have a similar taste, and wines which Alice likes should have a high chance that Bob also likes it. How do we do that now with the classical approach? And we can do that with an algorithm called singular value decomposition. The idea behind this algorithm is like to build it up in a matrix. So we have here a matrix, and each row represents like a wine, and each column represents a user. And we can see here, for example, that user 1 gave a rating to wine 1 with a value of 4. And we can see that user 1 gave a rating to wine 2 with a value of 2, and so on. And the question marks means that we don't have a rating for it. So the idea is we want to predict like the ratings we don't have in our matrix, and then we want to give like the highest prediction to the user as a recommendation. And if you think about not like an easy case like we have here, where we have just one user, just 4 users and 4 wines, but way more users. So we talk about 1 million users and 100,000 wines. We can assume that we have a very sparse matrix. So there are not that many actually ratings, because you can think not every user drank like all of the 100,000 wines. He drank maybe more than 5 or 10 or 20 wines. So like a lot of these entrants are missing. What do we want to do now? Actually, we can use like matrix factorization. So this is some kind of mathematical stuff you can do. And you can represent each matrix as by multiplying like 2 other matrices. And we are assuming here that we can actually use our rating matrix R and divide it into the matrices U and W. And W, of course, is transformed here. But how does this matrices actually look, and what do they mean? If we're taking our look at it, we can actually see that we are trying to model with the matrix U like the users. So we can give like each user like some kind of features. Here, for example, we try to model the user by taking 2 features and assigning like these features to every user. And again, we also want to do that for the wines. So we are trying to model like the wines, so the characteristics of the wines in some kind of way, by also representing it by 2 features. How do we now actually get like these features to get like good predictions? And we first have to think about what is a good prediction for us. And of course, we can use now these 2 matrices and predict like all the features or all the actually values inside of the R matrices, and also all the missing values. And the idea for a good prediction is if we are taking like the actually rated wines. So for example, wine 1 for user 1, and we are predicting like the value that we would assume user 1 would give to wine 1. And we can do that for all the values we have. And the idea is that we get a good prediction if like the distance between the actually values and the predicted values is quite low, because then we have like a realistic model which represents like the prediction or the rating of the user in a good way. But how can we do that now? And we can do that by using an algorithm which is called SDG, so stochastic gradient descent. And we're actually taking like all the predictions we have, all the ratings we have, calculating the prediction for them, and then we are adjusting like the features to minimize the difference between the actual values and the predicted values. And this is how we actually get then the features. And now if we have like the features vectors, we can actually predict like all the missing values and see what is coming out of it. And we can see, for example, that for user 1, we would predict a score for wine 3 of 4.1. And for user 1, we would predict a score for wine 4 of 3.7. So in our model, we would predict like, we would say like, okay, wine 3 is higher rated than wine 4. So we would recommend wine 3 earlier than wine 4 to the user 1. How could we do that now with a graph? And here again, we have to find the idea to find similar users. And what does similar users mean for us? It's not means that we are just liking the same wine. We also want to include like similar wines the user has liked. So the chance that like 2 users have drunk exactly the same wine when they have the same taste is not that high. But the chance that they have drank like similar wines is quite high. So again, we want to create like a model for this. And how do we do that? As you actually can remember from the collaborative filtering, we are trying to find like good embedding representations for all of the wine. So we are actually calculating like the fast random projection for all the wine nodes, and we are getting like embeddings for it. And now the idea of it is again to use like all of these embeddings, which we already have on the wines, and again, like doing a linear projection to create like an embedding for the user. So we are again like averaging all the wines or the wine embeddings, which some kind of way represents the characteristics of the wine, and again averaging them on the user to find out like what kind of wine does the user like. So what characteristics in a wine does the user like? We can see here an example. So we did that. We have like a user on the above. So the user 100292, and he rated some kind of wines. And we see that he has a high rating for the wine on the upper left-hand side. And we now see that we have like a pretty similar wine because the wine on the upper left-hand side and on the downer left-hand side share like a lot of characteristics. So these wines are pretty similar. So we are first like calculating the similarities or calculating the embeddings of the wine, and then we are calculating the characteristics of the user. And we can now see that we have like a similar 2H between these users because they like a similar kind of wine. And since the user also has rated this wine quite high, we would recommend this wine to the user above. Again, we have to take into account, of course, the similarity of the users, but also how good the other users rated the wine. Again, we created here some kind of example formula for the recommendation value. So here our recommendation score, for example, is 0.5 times the user similarity score plus 0.5 times the assigned rating. How can we now evaluate like all these things? And we have different kind of matrices to evaluate it. On one hand, we can use like predictive quality matrices, which measure the relevance of the recommendation. Of course, we require some kind of data set, which we can test the recommendations against. Here we have some kind of matrices that we can use. We can use the precision at K, the recall at K, or like some kind of average of precision and recall, the F1 score at K. We can also use ranking quality matrices, which measures the ranking of the recommendation. Again, we require a data set for this, which tests the ranking recommendations. Here we can use the matrices of mean reciprocal rank or the hit rate at K. And last but not least, the business matrices, so that measure the impact of the recommendation on the customer behavior. For example, the revenue, the click-through rate, or the conversion rate. Yeah, that's it. Of course, thanks to all of you to listen to my presentation, and I'm really open for questions. I see great talk so far. Thank you very much. Is there a link to the slides somewhere? I don't know if we have like a platform where we can upload these slides, but if yes, I think we will reach you out in advance and then I can send you the slides. Might be worth nothing that you can use any optimization algorithm, not just SGG. That's totally fine. Yes, we just take like SGD because it's, I think, one of the most famous like optimization algorithms, but of course, yeah, you can use other algorithms which are also like can be quite fast or very good. Regarding the relationship rate properties, is it fixed or can it be learned through prediction model fitting? Yeah, actually, the relationship property you are giving is like you can choose them. So, for example, if we have the rating, we would have like the values from 1 between 5 on our edges. And of course, this is something you mostly are doing with like some kind of business person. So you are actually talking to the guys who have like the business knowledge or the knowledge of the domain, maybe more talk about domain knowledge. And Jay can just say, okay, this should be like influenced more in a way. So you can, of course, customize like your algorithm or how you calculate embedding in such a good way. And that's also one big advantage of like the graph solution. You have on one hand, it's quite easy to understand. So it's not some kind of black box model, but you can directly understand what is influencing actually your similarity. And also you can customize like your stuff in a very easy and good way. And it's good to understand for like people who are not that technically and more coming from the business domain or from the business side. Did I understand it correctly that the graph-based approach is mostly on the content-based filtering part of your hybrid recommender? No, it's actually like a mix of it. So the graph-based approach first, if we are talking about the collaborative filtering, you are first like try to create embeddings like you did on the content-based filtering side. So you're creating like embeddings for the wines, and then you are using like all these embeddings again and try to calculate embeddings also for the users. So no, you're not only use it for the content-based filtering part of it, but also for the collaborative filtering part, because you're using like all the nodes in your network to calculate like good embeddings for your users, and also then calculating good similarities for your users. And Nicole said how to iterate the weights. Actually, you can use like the matrices. Also, if you have some kind of data set where you can test again and you are calculating like the matrices you have, then you can iterate the weight, for example, by using some kind of hyperparameter tuning. So you can say, okay, if I get good results, I'm fine. But if I get like not so good results, maybe you have to adjust the parameters in some kind of setting. So you can use some kind of hyperparameter tuning to improve the parameters. What GDS algorithm do you, sorry, that goes down, recommend when the data model is defined, but users have just started to post their data and now there's less data for recommendations in start? Actually, you can also try this one if you have like good features or stuff like this. The GDS algorithms that we are using is first like creating a projection, and then we are using like the fast random projection. So I would also recommend that to you. So first create like a projection of the stuff, and then you should use like the fast RP embeddings. And of course, if you have maybe users which haven't how do we maybe call it, interact in some kind of way with the system before, you can also leave like some kind of them out. This is also possible. So also sometimes it's useful to use some kind of subgraph. I guess you can also put your features into a more probabilistic classifier rather than fixing the score formula. Yeah, that's also possible. That's totally right. So if you have like a good thing for the score, you could also use like some other kind of classifier for it. So first maybe build the embeddings and then just do the classification based on a data set you maybe have. Okay, if we don't have any more questions, then thanks for all to listening to my talk, and enjoy the rest of the Nodes conference. And I want to give special thanks to my colleague Elena, because she created like the research project, but she got a newborn and can't present today. So maybe she's in the session. So bye-bye.